Okay, so let's get started. Everyone, please turn on your cameras. Hello, my name is Richard, and I'll be teaching today's lesson, and today's topic will be Boolean algebra. So Boolean algebra will be tested in ACSL contest number 3, so you have a lot of time to learn and practice this topic. I would like to remind everyone that contest 1 is, I believe, ending on January 14th. Or yeah, I think. So if you haven't started, you should start before that date. Okay. So Boolean algebra is the branch of algebra in which the values of the variables and constants have only two values, and those two values are true and false, and they are usually denoted as 1 and 0 respectively. Um, so in Boolean algebra, we will be performing operations with these variables, and the basic operators we'll be using are and, or, and not. So those are the three main operators you'll be using. And Boolean algebra has extensive applications in digital electronics, computer science, and information theory. It's also the foundation for designing logic gates, circuits, and algorithms. So they are definitely an important topic in computer science to learn about. Okay, so I'll start talking about the three basic operators, the first of which is and. So the and of two values is true only whenever both values are true. So it is usually written as xy or x times y, so similar to multiplication in math. And over here you can see a simple truth table, which shows the values of x, y, given different values of x and y. So because it's only true when both values are true, and remember 1 represents true, so the only case when xy is 1 is when both x and y are 1. In all other cases, x and y are 0 because both values are not true. Okay. Now the next operator is or. So the or of two values is true whenever either or both values are true. So it is written as x plus y. You'll see that later in the problems. So because we only need one of the values to be true, as long as it has a 1, it could be either x or y or both, then they should say x plus y. Then x plus y should be 1. Yeah, that's a mistake, but so for the or operator, if x and y are 0, then x plus y should be 0. And the last basic operator is not. The not of a value is its opposite. So basically this is negation. So the not of a true value is false and the not of a false value is true. So it is usually written as x with a bar on top, or sometimes you'll see like this dash or squiggly in front of the x. So here is a basic truth table for not. So this one only takes one variable. So we only have x here. So yeah, it's basically just the opposite value. Does anyone have any questions up to here? Okay, if not, then we'll move on. Okay, so there are some other operators. The first one is XOR. It stands for exclusive OR. So the XOR of two values is true whenever the values are different, and it uses the operator that looks like a circle with a plus sign in it. Yeah, so it's true whenever the values are different. So if we have a 0 and a 1, then the value is true. If we have 0, 0 and 1, 1, then the value is 0. And there is a property that we have to know for XOR, which is, so basically if we have A XOR B, this is the same thing as A and not B, or not A and B. So this, I could draw a truth table to illustrate it, but this preferably you should memorize it because you'll see this later on. Okay, so for three variables, it works the same thing, and we'll get to like order of operations like later on the next slide. But yeah, for three variables, you're still going to evaluate it for two variables, and then you'll take the result of that and then perform the operator with a third variable. So there are only two values, 1 and 0. So we'll get to problems later on where we'll have complex expressions, and you'll see how you can evaluate those. Yeah, so I'll draw a truth table to show this point. So, okay, let's say we have A and B, and then below we will see A XOR B, and then, so we know if A is 0 and B is 0, then A XOR B is 0. So this is just the stuff coming from the truth table over here, but we're trying to prove that it's also equal to A and not B, or not A and B. So if A is 0 and B is 1, then A XOR B is 1 because they are different. And whenever they're different, then the result is true. Same thing for 1 and 0. And then for 1 and 1, since they are the same, then A XOR B is 0. Okay, now let's evaluate each of these components separately. So this is A and not B. Okay, so for when A is 0 and B is 0, not B would be 1. So 0 and 1 would be 0. And then for the next one, we're evaluating A and not B for these two values of A and B. So let's first look at not B. Not B, since B is 1, so not B is 0. So 0 and 0 is still 0. And then for A equals 1 and B equals 0, not B would be 1. So A and not B would be 1 as well. And then for the last case, not B is 0. So this is also 0. And then I'll also do this one. I won't explain it since it's going to take a while, but you can do the truth table on your own, but this would be the value. And then lastly, let's compute this for, so basically we're taking the OR of these two. So it's going to be 0, 1, 1, 0. And so we see they are equivalent. So this is just like a simple proof for this theorem over here. Yeah. Okay, so next slide. The other operator that you should know is XNOR, which stands for exclusive NOR. So XNOR is the same thing as the opposite of XOR. So it's basically whenever the two values are the same, then the expression evaluates to true, and whenever they're different, then it evaluates to false. So it is the same thing as the not of the XOR function, and it uses the operator with like a circle and a dot inside. Okay, so this is XNOR. And then now we'll talk about the order of precedence. So when we have a large expression with many of these operators going on, we need to know which ones to evaluate first. So there is an order for this. Whenever we have an expression, we're always going to start with parentheses, and then after parentheses is going to be not. So whenever you see not, you should evaluate that first, and then you will evaluate and then after and, you will do XOR and XNOR, and finally you'll do OR. So OR is last in the order of precedence. And when we have operators that are in the same level of precedence, then they are evaluated from left to right, similar to your order of operations in math. And like ordinary algebra, we also use parentheses to group different terms. And when a not is represented with the with the line on top of the variable, with, yeah, the horizontal line, then there's an implicit grouping of the terms under the line. So basically what that means is, let's say we have A or B and there's a bar over it, then that's the same thing as like not A or B. This is what this is saying. So does anyone have any questions about the order of precedence? Okay, if not, then we will get into some fundamental identities that you should know when solving Boolean algebra problems. So there are two slides of these. The one on the first slide is relatively more straightforward. They're easier to see. And you don't have to know all the names. You just have to know what the identities are. So let's start with the first one, the commutative law. So this states that the order of application of two separate terms is not important. So basically, x or y is the same thing as y or x. X and y is the same thing as y and x. So we can switch the terms on either side of the operator and you will still get the same result. So this is similar to like the commutative law in just fundamental algebra. It just states that the order doesn't matter. And it's similar to the next one, which is the associative law. It's also a thing in algebra, which states that we can regroup the terms in the expression and it doesn't change the final value of the expression. So over here, there's parentheses around x or y. It's the same thing as if we put parentheses around the y and the z. And same thing, it applies to both the or operator and the and operator. Yeah, so remember the plus sign is the same thing as or, and multiplication is the same thing as and. The next one is idempotent law. Remember, you don't have to memorize any of the names. It's not super important. Basically, it says a term that is ored or anded with itself is equal to that term. So this is easy to see if we draw a simple truth table. So let's first look at the or case. So basically what it's saying is 1 or 1 is 1, 0 or 0 is 0. So it's pretty straightforward if you know the definition of or, and same thing for and. So 1 and 1 is 1 because both of the terms are true. So 1 is true. And 0 and 0 is 0 because if we want and to evaluate to 1, then both terms have to be 1. Yeah, so that is the idempotent law. The next one is the annihilator law, which says a term that is ORed with 1 is 1, and a term that is ANDed with 0 is 0. So this makes sense because in order for an expression that, for example, x or y, if we want it to evaluate to true, then one of them has to be 1. So anything that is ORed with 1 will give you 1 because only one of them need to be 1, and that's already given. So it doesn't matter what x is, it's always going to evaluate to 1. And that is similar to the one over here. So x and 0 is always going to be 0 because if we want the and to evaluate to true, then both of them have to be true. But we are already given that one of them is false, so it doesn't matter what x is, it's always going to evaluate to false. Next one is identity law, which states a term that is ORed with 0 or AND with 1 will always equal that term. So let's look at this case. So this one, it's easier to see with a truth table. So 1 or 0 is equal to 1 because one of them is true. And 0 or 0 is equal to 0. So basically the result is equal to the initial value of x, as you can see. So for x and 1 equals x, let's say x is 0, 0 and 1 is 0, because both of them have to be 1 in order for the result to be 1. And 1 is 1, since both of them are 1. So as you can see, the final value is also equal to the initial value of x when we are ANDing it with a 1. The next one is the complement law, which is pretty useful in some of the later questions. A term ORed with its complement equals 1, and a term ANDed with its complement equals 0. So complement basically is like the opposite. So the complement of 0 is 1, the complement of 1 is 0. So 1 or 0 is always going to be 1. That is, so whenever we're ORing two complements, it's going to be 1. And then whenever we're ANDing two complements, like 1 and 0 or 0 and 1, the order doesn't matter because of the commutative law. It's always going to be 0 because if it were to be 1, then both values have to be 1. But since we are ANDing two complements, they can't be both 1. So that is what the complement law is saying. So does anyone have any questions? Okay, the dot means multiplication. So the dot is basically and. Is 0 and 1 still 1? So 0 and 1 is 0, since both terms have to be 1, going back to the truth table for and. So all of them, both x and y have to be 1 in order for x, y to be 1. So does that answer your question? Okay. So let's move on to some more complicated identities. So the first one is the absorptive law, which it's just referring to how we can absorb like terms and basically simplify a more complex expression like x or x and y. So you don't have to memorize this one either. You can easily prove it. So I'm actually going to skip to the next one, distributive law, because we're actually going to use that to prove this one over here. So distributive law is basically the same thing as in algebra. We can multiply out something like this. So you can also do like, you can also FOIL them, and you can also, this one is different, but you can factor and you can distribute. That is what this one is saying. So now let's try to prove this one. So let's try to factor the term on the left side. So that will give you x times 1 plus y. So inside here, we have 1 or y. So going back to the previous identities, which one is it? The annihilator law. It says whenever a term is ORed with 1, it's always going to be 1. So we know this is always going to evaluate to 1. So basically we have x times 1. So x and 1 is always going to be x. So that basically proves this statement. And then for the next one, so we can distribute the terms on the left. So we have x and x. X and x is just x. So we have x plus xy. So this is actually the same. These two are actually equivalent. So this one is harder to understand. Does anyone have any questions? Okay. The next law is super useful, and this one, you probably should know the name. It's De Morgan's law, which basically says an or and expression that is negated is equal to the and or of the negation of each term. So basically, we have x or y, but we want to not the whole thing. be careful here. Many of you may assume this is equal to just this, but you cannot break apart this expression. De Morgan's law states instead of or over here, it should be and. So basically, we have to flip the operation. And so we can break apart this bar on top by applying it to each variable, but we have to flip the operation in the middle. So that also applies for not x and y. So we can um, apply the negation to each variable, but we have to flip the operation. So that is De Morgan's law. It's super useful when we're solving problems. Now the next one is, I think, the most obvious one, double negation. A term that is inverted twice is equal to the original term. So not x is just x. And lastly, the relationship between XOR and XNOR. So XOR and XNOR are like the opposite. So x um, x XNOR y is the same thing as not x XOR y. And we can also apply the not to each individual term. It will still give you the same result. This one um, isn't really used a lot, but it's still good to know that XOR and XNOR are opposites. But you can also just see that from the truth table over here. XOR is whenever the values are different, it's true. And XNOR is whenever the values are the same, it's true. So they are opposites of each other. Now let's do some practice problems. And you will use a lot of these uh, identities. So the first question I want you to try on your own, this is like a warm-up question. It's not that hard. Okay, I'll give you guys some time to work on it and then I'll go over it. So someone asked, what is the squiggly line? I think you're referring to the second question, but the squiggly line is the same thing as not. So the plus sign is or, the multiplication sign is and. Okay, I see some answers and some questions. Inclusive means including. So whole numbers 1 through 13 inclusive, that includes 1 and 13. If it says exclusive, then we don't include them. So for the first question, let's first evaluate this chunk over here. So following the order of operations, actually order of operations says to do not first, but let's just do this first part first because the or basically separates these two expressions. So on the left side, x has to be greater than or equal to 6 and less than 8. So the only two possible values would be 6 and 7. And here's where some of you made a mistake. On the right side, not x is less than 10 is the same thing as x is greater than or equal to 10. So do not forget 10 over here. This is a common mistake. So when we're negating x is less than 10, it's x is greater than or equal to 10. So and we're also given that it has to be through 13 inclusive. So this gives us 10, 11, 12, and 13 as the values that satisfy this expression. So altogether, there are 6 values that satisfy this Boolean expression. So question 1 should be C. And then for the next question, this one requires De Morgan's law. So for question 2, I don't really like the squiggly notation. It's kind of harder to see, so I'll use the horizontal bar notation. So this is okay, this is not A and not B. So okay, if we are to evaluate this, oops, this is, so we can negate each term and then flip the sign. And then for the second term over here, it's not A or B. So we can negate each term and then flip the sign. So the addition becomes multiplication. And when I don't write anything in between, it's basically and or multiplication. Okay, so now we need to find A or B, which comes from here, or not A and not B, which comes from here. Okay, so we can evaluate like each term individually. So we want the whole expression to be true. So since we're ORing 3 terms together, as long as one of them is true, then the whole thing is true. So we can consider each term separately. So for example, if A is true, then the whole thing is true. So A is true for 1, 0 and 1, 1. So I'm basically like using ordered pairs. So you can think of it about like, you can think of it as A comma B. So A is true for 1, 0 and 1, 1. And then B is true for 0, 1, 1, 1. Basically, whenever B is true, then the whole thing is true. And then lastly, let's consider the last term. This is true for only 0, 0. So basically, all the pairs work. So we have 1, 0, 1, 1, 0, 1, and 0, 0. So all 4 pairs work. So the answer is E. Yes. Okay, so moving on. Um, I'll do the first question and then you guys can try the second one on your own. Let me clear. I don't know why it's not clearing the annotations. Okay. Yeah, so what is tautology for the second question? A tautology is basically an expression that is always true. So for question 5, it's asking which of the following expressions is not guaranteed to be always true, basically. For the first question, let's first evaluate the term on the left. We can distribute the terms. So for the first part, we get not AB. So I'm multiplying not A and B by not A. So not A times not A is just not A. This is one of the identities. So whenever you and something by itself, it's just itself. So we can get rid of one copy of not A. And then let's distribute this, the not B over here. So it would be not A, B times not B. So B and not B is always going to be false. So this whole term here is 0. So we can basically get rid of it. And then now let's distribute the next expression. So we have A not B, not A. So same thing. A and not A is 0. And then lastly, we have A not B times not B, but not B times not B is just not B, so we can get rid of that, one of those. So this is equal to not AB, and then the ones that are 0, we can disregard them, or not, or A and not B. So the answer should be B. Yeah, the answer choice just reversed the two expressions. I'll give you guys some time to try question 5, and then I'll go over it. Okay, so this one seems to be a bit trickier since a lot of you couldn't get it. The correct answer is C. So basically A, B, and D are all tautologies. Only C is the one that is not always true. So how I would approach this is we can basically evaluate each of the answer choices and see if they come down to true or not. So for answer choice A, um, first thing I see is in the parentheses, we have not B or B. So when two complements are ORed together, it's always going to be one. So this whole thing is one. So we have A and one or not A. So A and one is the same thing as A. So basically we have A or not A. And whenever um, something is ORed with its complement, it's always going to be true. So answer choice A is always going to be true, so it is a tautology. So we can eliminate choice A. Now let's move on to choice B and do the same thing. So for B, I see A or B is common, and one of them has a negation in front of it. So basically you can treat A plus B as one term. So let's call it X. So basically we have not X or X. So it doesn't matter what A plus B is, but we are ORing two complements. So this is always going to be one. So it doesn't matter what A plus B is, since we are ORing two complements, it's always going to be true. So B is not the answer, it is a tautology. And C. So let's try to evaluate C. So for C, we have parentheses, so we can distribute it. So we have A, not B. So since we have two A's, A and A is just A, so we can leave out one of them. A and not B, and then let's distribute the second term, which is B, not A. So in case you're confused, B, not A, B is just B, not A, since we can consolidate the two B's into one B, because B and B is always going to be B. That is one of the identities. Oops. So answer choice C evaluates to A and not B, or B and not A. So we can't simplify it anymore. So C is the correct answer, but let's just check D to make sure. So for D, um, let's see. Okay, so these two terms have a B in common. So let's factor out a B and see what we can do. So we have A or not A. So A or not A is always going to be 1 because they are complements, or not B. So this is the same thing as B or not B. And you'll notice this is the same case as in answer choice A, so this is always going to be true. So therefore, C is the correct answer because we cannot guarantee it will always be true. It doesn't mean it can't be true, it just means it isn't always true. Does anyone have any questions? Okay, if not, we will move on. So question 1. We're moving on to junior division. So we graduated from elementary. Now let's practice some junior division questions. Question 1, simplify this Boolean algebra, this Boolean expression, and question 2, how many ordered pairs make the following expression true? So most of you got question 1 correct, but seems like question 2 was a bit trickier. So for question one, we can simply remove the parentheses since they don't really do anything. And then we have B or B. So we can consolidate that into one term since B or B is just B. That is one of the identities. So this is the same thing as A or AB or B. And then this, for A or AB, we can use the absorptive law to combine them into A. So this is just A. If you forgot what the absorptive law is, you can prove it by just factoring out an A. So it becomes A and parentheses 1 or B. 1 or B is always 1. So this whole term is just A. So it evaluates to A or B. So D is correct for question 1. And for question 2, we have terms that are in parentheses. So the best way to go about this is to distribute. So we have A, not A, B, A, or not A, B, not B. So not A and A is always going to give you 0. So it doesn't matter what the value of B is, this whole term is 0. Same thing, B and not B, whenever you're anding something and its complement, it will always give you 0. So it's going to be 0 or 0 since both terms are 0. So it simplifies down to 0. So this will always be false. So no terms will make the expression true. So the answer is 0. A for question 2. Does anyone have any questions? Okay, if not, then we will move on. Now this is intermediate division. I'll give you guys some time to do it and then I'll go over it. Okay, now let's do question 1 together. So once again, we have parentheses here, so let's distribute. So we have A, not A, sorry, not A and A plus not A, not B plus not A, B. Okay, so the first term, not A and A, is always going to evaluate to 0 because we are doing A and its complement. So this is always 0. And then the next two terms, at first it may seem like we can't really simplify them anymore, but you'll notice not A is common in both of them. So let's go ahead and factor that out. So this is 0 from the first term, and or not A, not B, or B. So now we can evaluate the inside of the parentheses. This is always going to be 1 since we are ORing B and its complement. So so the answer is just not A. So the answer for question 1 is B. And question 2 is a bit more complicated, so I'll save it for next week. It involves 3 variables, yeah. So that is it for today's lesson. Does anyone have any more questions? Okay, if not, then hope you all have a great week, and please be sure to complete contest 1 before the deadline. Thank you.
Bye.
Bye.